In this episode, we will talk about InternVL3, exploring advanced training and test time recipes for open source multimodal models.
Sounds good. It's a pretty exciting development in the MLM space.
Yeah, definitely. We're taking a deep dive into these multimodal large language models,
Yeah.
MLMs for short. Um, these are systems trying to understand the world more like we do, right? Processing text, images, maybe other things too.
Exactly. It's a big step towards that idea of artificial general intelligence, AGI, combining different senses, basically.
Now, what's kind of interesting or maybe inefficient is how many current MLMs, both open source and the big proprietary ones, they started out as just text models.
They were language models first, and then vision capabilities were sort of bolted on afterward.
Right, like teaching an old dog new tricks maybe.
Yeah.
Works, but it can lead to problems getting vision and language to really sync up properly. This add-on approach creates alignment challenges.
Precisely. That after-the-fact training, grafting vision onto an already trained language model,
Yeah.
it's tricky. We call it the alignment challenge.
Like translating between two really different ways of thinking.
Yeah, that's a good analogy. You might get the literal translation, but lose the nuance, the deeper connection between the modalities.
Okay, and trying to bridge that gap often means needing specialized data, right? Like for reading text in images, OCR.
Yes, optical character recognition data helps, and you often need these really complex training schedules.
Complex how?
Well, you might have to freeze parts of the model, say keep the language part fixed while you train the vision adapter, or go through multiple fine-tuning stages, all to try and add vision without breaking the language skills.
And that sounds expensive, computationally demanding.
It absolutely can be very resource intensive, which really highlights that maybe it's not the most, let's say, elegant or efficient way to build a model that's truly multimodal from the ground up.
Which brings us nicely to InternVL3. They take a totally different approach, don't they?
They do. Their philosophy is what they call native multimodal pre-training.
Native multimodal pre-training. Okay, what does that mean in practice?
It means that right from the beginning, in that initial huge pre-training phase, the model learns to understand text and visual information together simultaneously.
So it's not text then vision. It's text and vision from day one.
Exactly. It learns to see and understand language in context together right from the start. Joint learning.
Okay, so this core idea, joint learning, it avoids adding vision as an afterthought. It's baked in.
Precisely. That unified pre-training is much more streamlined. It avoids all those complex multi-stage alignment fixes you see in the, let's call it, traditional post-hoc approach. It's just a more integrated way to learn.
Now, the paper mentions a VT MLP LLM architecture. Can you break that down a bit?
Sure, it's the structure they use, similar to earlier InternVL models. Three main parts. VIT is the vision transformer. That's what processes the image pixels, the seeing part.
Okay.
Then the MLP, a multi-layer perceptron. Think of it as a bridge, connecting the visual info from the VIT to the language part.
And the LLM is the large language model, handling the text.
Correct. Now, for InternVL3, the VIT and LLM parts start with weights from powerful pre-trained models like InternVT, Quinn, InternLM3, but crucially, not versions already fine-tuned for instructions at this stage. The MLP bridge, though, starts fresh with random weights.
Got it. And they do something called pixel unshuffle for high-res images. What's that about?
Yeah, pixel unshuffle. It's a clever trick for efficiency. Instead of processing every single pixel, it rearranges pixels within an image tile. So for example, a 448 by 448 pixel tile gets condensed down into just 256 visual tokens.
So fewer visual pieces for the model to handle.
Exactly. It makes processing high-resolution images much more scalable, which is really important when you need fine detail.
Okay, this sounds really foundational. Now, one of their specific new ideas is variable visual position encoding, or V2PE. Sounds complex.
It does sound a bit technical, but the concept is quite smart, especially for handling long sequences with both text and images mixed together.
How does it work differently from normal position encoding?
Okay, so normally position encoding just tells the model the order of tokens, right? Like word 1, word 2, image patch 1, image patch 2. And each step increases the position index by 1. Uniformly.
Right.
V2PE changes that. It uses a different way to calculate the position index for visual tokens compared to text tokens. Text tokens still increment by 1.
But visual
Tokens increment by a smaller fractional value, which they call delta. So AE is always less than 1.
Interesting. So the position clock ticks slower for visual information within the sequence. And how is delta decided?
Well, for any single image, delta stays the same. But during training for each new image, the model randomly picks a delta value from a set like 1, 12, 14, all the way down to 1256.
Whoa, there's a big range. Why
Yeah.
do that? What's the benefit?
The big benefit is handling much longer multimodal contexts. You can have more text and more images without the total position index getting incredibly large, which can cause problems for models. It stretches the effective context window.
Ah, so it compresses the positional space for images.
Kind of, yeah. And during inference, when you're actually using the model, you can even adjust delta based on how long your input is to balance performance and context range. If you set delta to 1, it just acts like the old positional encoding. Very flexible.
That is clever. Really clever way to tackle long inputs.
Yeah.
Okay, let's dive deeper into the native multimodal pre-training itself. You mentioned it's autoregressive.
Yes, it uses a multimodal autoregressive formulation. Think of the model processing a stream of mixed text, image, and even video tokens, left to right, always trying to predict the next token based on all the previous ones.
So when it's learning, the error signals, the gradients, they flow back through both the text and the visual parts.
I do. Gradients propagate through everything. But, and this is key, the actual loss, the thing the model tries to minimize, is calculated only based on the text tokens.
Only text tokens. So it's not explicitly trying to predict, say, the next patch of an image.
Correct. The visual tokens act as context. They provide the information needed to predict the text better. This forces the model to embed that visual information in a way that's useful for language generation. It has to understand the image to talk about it.
That makes intuitive sense. Force it to understand vision in service of language. What about token weights? The paper mentions that too.
Right. Simply averaging the loss across all tokens or samples can sometimes bias the model towards, say, always giving short answers or always long ones. InternVL3 uses something called square averaging for the loss, which helps mitigate these biases towards specific response lengths.
And unlike the post-hoc methods where parts might be frozen, here, all the model parameters are updated together during pre-training.
Yes, that's the joint parameter optimization. The VIT, the MLP, the LLM, everything is trained end-to-end simultaneously on this combined data set of text-only and multimodal data. It ensures the visual and linguistic representations are learned in a coordinated way.
Speaking of the data, what are they trained it on? Sounds like it needs a massive, diverse diet.
It certainly is. They built on the InternVL 2.5 data image captioning, visual QA, math, OCR, documents, but updated the components and framework. And crucially, they added lots of new real-world data.
Like what kind of real-world data?
Things like understanding graphical user interfaces, GUIs, using tools based on instructions, 3D scene understanding, and video data, really pushing into more complex interactive domains.
And they still included pure text data, too, to keep the language skills sharp.
Absolutely. They incorporated a lot of language data based on InternLM 2.5's pre-training corpus plus other open-source text data sets, specifically to boost knowledge, reasoning, math, and general language fluency.
How did they balance the mix between the text-only stuff and the multimodal stuff?
They did some experiments and landed on a two-stage sampling strategy. They figured out the best way to sample within multimodal data and within language data separately first. Then they tested different overall ratios and found that a 1:3 ratio worked best 1 part language data for every 3 parts multimodal data.
So about 50 billion language tokens and 150 billion multimodal tokens for around 200 billion total.
That's the scale, yes. A huge amount of diverse data fueling that native pre-training.
Okay, so that's the foundational pre-training.
Yeah.
But they don't stop there. There's post-training refinement too, right?
Correct. A two-stage post-training strategy. First is supervised fine-tuning, SFT. Second is mixed preference optimization, MPO.
SFT, that's pretty standard. Training on good input-output examples.
Yes, but the key advancement for InternVL3's SFT was the quality and diversity of that data. They really expanded the SFT dataset with more examples covering those complex areas. Tool use, 3D, GUI, long context video, scientific diagrams, creative writing, multimodal reasoning, really broadening its capabilities. They kept some techniques from InternVL 2.5 too, like random JPEG compression for robustness.
Okay, better SFT data. Then comes MPO, mixed preference optimization. What problem does that solve?
MPO tackles a subtle but important issue, the difference between training and inference. During training, pre-training in SFT, the model predicts the next token based on the correct previous tokens from the data.
Right, the ground truth.
But during inference, when it's generating text freely, it predicts based on the tokens it just generated. This difference, this distribution shift, can hurt its ability to do complex step-by-step reasoning, like chain of thought, COT.
Ah, because it might go slightly off track based on its own previous output.
Exactly. MPO tries to bridge this gap. It adds supervision based on comparing chosen good responses and rejected bad responses.
How does it do that? What's the mixed part?
The MPO loss combines three things. One is a preference loss using DPO direct preference optimization, which explicitly teaches the model to prefer the chosen answer over the rejected one.
Okay, learn from comparisons.
Two is a quality loss using BCO binary cross-entropy optimization. This helps the model judge the absolute quality of both chosen and rejected responses.
So understand not just better, but also good and bad.
Precisely. And third is just the standard generation loss, the language modeling objective to keep improving fluency, especially for the preferred responses.
And where do they get these pairs of good and bad responses for MPO?
They used a dataset called MMPR v1.2, about 300,000 samples covering VQA, science, charts, math, OCR, documents. They generated the chosen rejected pairs using the SFT versions of their own InternVL3 models at different sizes. So the models learn from their own potential outputs, guided by this preference data.
Okay, that covers pre-training and post-training. But there's also something they do at test time scaling.
Yes. Another layer to boost performance, particularly for reasoning tasks without more training, they use a best of n evaluation strategy.
Best N. So generate multiple answers and pick the best one.
Exactly. The model generates n different potential responses or reasoning paths for a given problem.
And how do they pick the winner?
They use a separate critic model called Visual PRM 8B. Its job is specifically to evaluate the quality of these n responses, especially for reasoning and math problems, and select the best one.
A dedicated judge. How does Visual PRM score the responses?
It looks at the solution step by step. For each step in the reasoning chain, it assigns a quality score. The overall score for a response is the average of these step scores. The score for a step is basically the probability that the model would generate a plus symbol, which signifies a correct or good step in their setup.
Clever. How do they train this Visual PRM judge?
On a dataset called Visual PRM 400K, it was built using questions from that MMPR dataset again, but expanded with lots of different solution attempts, rollouts, generated by the InternVL3 models themselves. This gave Visual PRM plenty of examples of good and flawed reasoning to learn from.
It really sounds like they've optimized at every single stage, pre-training, post-training, and even test time. And underpinning all this must be some serious engineering for the training infrastructure.
Oh, absolutely. They significantly enhanced their InternEVO framework, which was already designed for efficiently training massive models using techniques like Zero. They adapted it specifically for the VT-MLP LLM structure of InternVL,
allowing them to scale to hundreds of billions of parameters, thousands of GPUs.
That's the scale, yes. Key optimizations included flexible ways to split or shard the different model components, VIT, MLP, LLM, across GPUs. This allows overlapping communication and computation, making things faster.
And they support various ways to parallelize the training.
Yes, data parallelism, tensor parallelism, sequence parallelism, pipeline parallelism, and combinations of these. They also tackled the challenge of varying amounts of visual versus text data, potentially unbalancing the workload across GPUs.
Oh.
They built in dynamic load balancing techniques to keep all the GPUs busy and efficient, regardless of the input mix. Plus, lots of work minimizing memory usage and communication overhead, and specialized techniques for handling super long sequences, up to 32K tokens.
And the payoff? Did it make training faster?
Significantly. They reported speedups of 50% to 200% for InternVL3 compared to training similar size InternVL 2.5 models on the same hardware. That's a huge efficiency gain, essential for making these massive training runs feasible.
All right, the moment we've been building up to, the results. After all that innovation, how good is InternVL3?
The results are, frankly, stellar across the board. The headline number is probably the InternVL3 78B model, scoring 72.2 on the MMMU benchmark.
MMU. That's a tough, comprehensive, multimodal benchmark.
Well, extremely tough. That score sets a new state-of-the-art for open-source MLLMs, and importantly, it puts it right up there, competing directly with leading proprietary models like ChatGPT 4o, Claude 3.5 Sonnet, and Gemini 2.5 Pro.
Wow. Competitive with the closed-source giants while being open source, that's huge. And it didn't forget how to do language either.
Nope, they emphasize it maintains strong pure language abilities too.
The paper has tons of tables. Can you give us the highlights across different areas, overall performance?
Sure. Overall, big improvements across many benchmarks compared to previous versions and competitors. This is down to the better training, testing, data, the whole package. It even beat the closed models on some specific things like diagram understanding, AI2D, and chart QA. Gemini 2.5 Pro did edge it out on hallucination detection, though.
How about those core reasoning and math skills?
Very strong performance there, too, on benchmarks like MathVista, MathVerse, LogicVista, clear gains with bigger model sizes, and that best event evaluation with visual PRM really boosted the reasoning scores significantly.
And reading text and images, understanding documents, charts, OCR stuff.
Robust performance, often superior, especially on documents and charts where that native pre-training likely helps a lot. The big 78B model got really high scores on OCR bench and visual common sense reasoning, VCR.
What about tricky stuff like reasoning across multiple images?
Consistent improvements over older models there, especially noticeable even at the smaller 2B scale. The 78B model was competitive with GPT-4o, though some gaps remained on certain multi-image benchmarks.
And understanding real-world situations.
Promising results even for the small 1B model, scaling up nicely. The 78B model held its own against GPT-4o, even beating it on one real-world benchmark.
Okay, comprehensive evils, hallucination checks.
On broad multimodal benchmarks like MME and MM*, the larger InternVL3 models generally came out on top compared to other big open-source models. For hallucinations, performance was competitive and improved over older versions. But, like I said, still an area with room for refinement based on some specific benchmark results.
Visual grounding, linking text to image regions.
Good performance, improved with scale, but seemed to plateau a bit at the very top end. They suspect maybe their training data wasn't quite specific enough for grounding tasks at that extreme.
And languages other than English. Multilingual.
Consistent improvements there, too, compared to predecessors. The larger models were competitive with or better than other strong multilingual MLLMs, like InternVL3
Video, GUIs. They tested everything.
Pretty much. Clear improvements in scaling and video understanding across several benchmarks, and competitive results in GUI grounding, sometimes beating other leading models.
Really sounds like a powerhouse model, performing strongly just about everywhere. And the commitment to open science is key here.
Absolutely. Releasing the training data and the model weights is a huge contribution. Their stated goal is explicitly to foster more research and development within the open source community.
So, wrapping it all up. InternVL3's core innovation is that native multimodal pre-training tackling alignment head-on, enhanced by V2PE for long contexts, sophisticated post-training with SFT and MPO, and boosted further by test time scaling.
And the result is state-of-the-art open source performance, genuinely competitive with the best closed systems out there. A major step for open multimodal AI.
Which leads us to a final thought for you, our listeners. With the release of InternVL3's data and model weights, what new applications and research directions do you think will emerge in the field of multimodal AI, now that such advanced capabilities are more openly available?
It's exciting to think about what the community will build with this.
Definitely. We encourage you to delve deeper into the released resources and continue exploring the fascinating advancements in multimodal AI.